Everything we do, all the estimates of health effects, decisions on the need for mitigation, development of new construction standards, all of that is based on individual measurements that are made. I had the great honor these past 3 years to serve with Phil Jenkins and the people listed here on the committee. This standard has been 26 years in the making, and it is not possible that this standard could have been developed without these people, as well as people who commented on the standard. This definitely is a consensus standard and benefits greatly from both the people who run radon chambers as well as radon instrument manufacturers and distributors. We wanted very much to make this standard immediately useful and usable for people. Performance criteria really are not that useful unless you provide a framework for testing. In other words, how well devices perform is one thing, but you also need to provide instructions for how to prove how well they perform. The performance criteria involve a lot of terms, so we have several pages in the standard where we have definitions, including a standard test atmosphere for radon, or a STAR chamber, and that term we picked up from the international standards that have used that term to mean a radon testing environment. We also provide definitions of device categories, and most contentiously the category of continuous radon monitors, and the definitions of device categories are not exclusive, so as new technology is developed, they can fit into these device categories. And then minimum detectable concentration, which is extremely important because, of course, we are measuring at relatively low concentrations, at least compared to background. So minimum detectable concentration is important. All that, and the standard is only 14 pages long. You can see that we have definitions, including classifications in continuous radon monitors, integrating methods, and equilibrating methods. The criteria are described in section 7, where we've got accuracy and precision, minimum detectable concentration, proportionality, and then criteria for performance in different temperature and humidity environments. And then last but not least, a description including an example report of documentation to prove that a device meets the criteria of this standard. These criteria are primarily for residential and office environments, and they're not for special situations such as handling radioactive materials where other regulations are going to apply. They are criteria for total error or accuracy, imprecision, and minimum detectable concentrations in various radon concentration environments, various temperature, and various humidity environments. This standard itself is not a description of a proficiency program, but it could be used as a rubric that a proficiency program could adopt. The performance criteria are criteria that can be satisfied by existing data. So obviously, if you are a radon measurement development company, you will be doing tests and you will have a plethora of data that could be used to prove that your devices meet these criteria. The criteria are not designed to force extensive additional testing at all. As long as appropriate documentation is provided, existing data should be able to demonstrate adherence to the standard. Again, it doesn't restrict mechanisms or designs, so it is intended to be useful even as we hope new technology is developed. These are explicitly defined statements of sets of conditions under which performance is tested and reported, but we don't get into calibration or quality assurance. There will be future standards that may look at QA and QC. These are criteria that are applicable to methods used to make decisions on the need for mitigation. However, these performance standards are not intended for measurements used for diagnostic purposes, for example, less than 1 hour duration measurements. Those are ongoing in the field type measurements, and that's not what these performance criteria are intended for. The first category, continuous radon monitors. The definition states that continuous radon monitors provide numeric reviewable values, that the minimum detectable concentration is less than or equal to 4 picocuries per liter for 1 hour measurements, and that the calibration factor is greater than or equal to 2 counts per hour per picocurie per liter. And the calibration factor, as is always defined, is the response divided by the concentration. In other words, it's the signal divided by the input. This definition may include, but it isn't exclusive of other designs, scintillation cells, ion chambers, and solid-state-based devices. The integrating method category includes those devices that collect and accumulate an ongoing signal, and the result represents the average concentration during exposure. And this device type may include electrets, alpha track detectors is probably the biggest example, and then electronic devices. Now, one critical thing for these device categories is that to comply with the standard, the device cannot display results for time periods less than that for which it has met the criteria. So in other words, devices that print or store or display results hourly but don't meet the continuous monitor definition would be categorized as electronic integrating devices. Equilibrating methods. These are devices that may use the adsorption of radon as the operating principle. They're not true integrating mechanisms. They function using the physical principle of equilibrium, which is constantly being sought between the radon absorbed and the radon in the environment. There may be some dependency on temperature and humidity, depending upon the designs, which sometimes slow the desorption. And the analysis of these devices may include gamma spec or liquid scintillation. But again, the categories are not exclusive of other methods. What are the requirements? This is a picture of a chamber. Remember, total error, which is also called accuracy, includes both imprecision and bias. And imprecision is the random component of error that, for example, if you've got 5 identical devices, would produce results that are slightly different between the responses of the 5 devices, because try as you might, you cannot make something identical. Or when you've got one device and it's monitoring the same concentration, it wiggles slightly in its response, because of course we live in the real world where nothing is perfect, and as try as you might, you're never going to get something perfectly measured and be perfectly stable. So the precision error is one component of accuracy. Then also you've got bias, which is the systematic component of uncertainty, and bias is like the jump. So remember, precision is like the wiggle, and bias is like the jump. Bias in general results from a calibration error, where it's calibrated slightly high or slightly low. It may also be a factor of drift or something systematic. The device gets bumped and everything is low after that point in time. Both of those components of error go into total error or accuracy, and our requirement is that a group of 5 devices be simultaneously exposed to a radon concentration of between 6 and 15 picocuries per liter, 65 to 75 degree Fahrenheit, 10 to 55% relative humidity, and each device must be within plus or minus 25% of the average radon concentration, and that is called the individual percent error. So each one of these devices must be within plus or minus 25% of the known radon concentration in the chamber during the exposure. That's the first requirement. The second is for precision. So remember, precision is one component of that total error. Precision is the random component of error, which try as you might, you cannot eliminate, because you could not possibly make 5 devices perfectly exactly. There will be slight differences between them. That's the random component of error, and that also must be tested for, because you don't want your devices to be all over the place and be inconsistent. So it's the same conditions in the radon chamber, 6 to 15 picocuries per liter, 65 to 75 degrees Fahrenheit, 10 to 55% relative humidity. In this case, the criterion is based upon the average of the 5 devices. If you look at the results from the individual devices, you calculate the sample standard deviation, you divide by the mean, that's the coefficient of variation, and that has to be less than or equal to plus or minus 15%. That's the second requirement in the standard, is for the precision. Proportionality criterion is that the average of the individual differences at the low concentration minus the average of the individual differences from the known radon concentration at the high concentration must be within plus or minus 15%. And what that looks at is how this line can tilt, how far this line can tilt and be off high or low. So looking at various possibilities, if you've got an average individual percent error low of minus 10% and an average individual percent error high of plus 5%, it would pass the proportionality criterion. If it's reversed and you're 5% high at the low end and then 10% low at the high end, it would still pass the proportionality criterion. However, if the low is high 10% and the high is low 10%, it would fail the proportionality criterion at both ends of the range of low to high. So that's the third criterion. Then we get into a bit more nitty-gritty with the minimum detectable concentration. MDC, minimum detectable concentration, is based on the variability of background. Because if, for example, you have a background that's very high, but it's totally stable, it's always 100 millivolts, say, then there's no problem because you always subtract off 100 millivolts. And you can have a really low minimum detectable concentration because your background is very stable. However, if your background is all over the place, sometimes it's 100 and sometimes it's 50, then you are in a worse situation in terms of your minimum detectable concentration because you don't know if when you measure a relatively low concentration, is that a signal due to actual radon concentration or is that a signal just due to the fact that your noise is high at that particular point in time. So the calculation of minimum detectable concentration is based on the variability of the background. The tests are what are called blanks, or exposure in aged air or nitrogen, and the criterion is derived from being 95% confident that there's a signal that is detectable over the noise of the background. The requirement is that if the minimum measurement duration recommended by the provider is 1 hour, then the MDC needs to be 4 picocuries per liter or less. If the minimum measurement duration recommended by the provider is 2 days or more, then the MDC needs to be 1 picocurie per liter or less to meet the requirements of the standard. Then, temperature. The requirement for temperature is that you want to keep the radon concentration relatively high so that it doesn't confound the effective temperature, and you want the relative humidity stable and in a relatively low range. And then you expose 5 devices at a low temperature, 5 devices at a high temperature. The criteria are the same as for the accuracy. So the 5 devices must have a coefficient of variation of less than or equal to plus or minus 15% to minimize the imprecision. And for total error, each individual device out of the set of 5 exposed at low temperatures and high temperatures needs to be within 25% of the average radon concentration during the chamber, average radon concentration in the chamber during the exposure. Relative humidity, the same sort of idea. You keep radon concentration high so that it doesn't confound the effect of relative humidity. You keep temperature stable in a room temperature. Then you have a set of 5 devices exposed at a low relative humidity of 15 to 25% and a set of 5 devices exposed at a high relative humidity, 70 to 80% relative humidity. And then the criterion are the same. The imprecision, as measured by the coefficient of variation, has to be within plus or minus 15%. And then the total error is that each device must be within 25% of the average radon concentration. The status of the standard now is that we incorporated the first round of comments, and they were very valuable. All the comments are taken very seriously and have improved the standard. So thank you very much for those of you who have commented. We are now incorporating the second round of comments. This standard isn't a done deal. It will be evaluated for revisions every 5 years, and the intent is to encourage more measurements and improve public health.